Hey there! On today's episode of Aftermath, we're in lesson 39 in our algebra books, and we're going to look at a couple different things. There's actually 3 parts in the lesson in the book, but the first 2 parts go together very closely, so I'm going to treat them as one. It starts off talking about what's known as the trichotomy axiom, and this is one of those things that we have in math that sounds very, very complicated, but it's for a very simple thing. And that thing is simply that when we compare any 2 numbers, if we just pick 2 random numbers and compare them, then one of 3 things has to be true. Either one of those numbers is greater than the other one of those numbers is less than the other one, or one of those numbers is equal to the other one. So it's a very, very simple thing with a really horrible sounding name, right? But we're going to use it for the second part of the lesson today. The second part of the lesson is on negated inequalities. And again, this is something that sounds bad, but it really isn't if we use that axiom we just talked about. This is an example of a negated inequality right here. Now, if we pretended that this slash was not through it, and it was just a normal inequality like we're used to, it would say x is greater than 10. And we're used to that. That's just saying that x is some number that's bigger than 10. Well, this has a slash through it, so that's telling us that it is not whatever this is. So it is actually saying x is not greater than 10. And based on the axiom that we just looked at, that we just learned about, if x is not greater than 10, then there are only 2 other possibilities that it could be. The only other 2 possibilities are that x could be less than or equal to 10. And so when we see x is not greater than 10, we need to go ahead and change that. This is a negated inequality. We need to change it to a regular inequality, and that would be x is less than or equal to 10. Because after all, if it's not greater than, it has to be one of those 2 other things. And then we can go ahead and graph it like we normally would. We've learned how to do that before. If I want to show all the numbers less than or equal to 10, I would draw a number line. And I'm going to start with 6 on my number line and just go on up to 11. Because anytime you can kick it up to 11, you should, right? So I've got my 11 there. I didn't actually need to go that high, but there it is. So I want to represent that x is less than or equal to 10. So on my number line, I'm going to start with 10. And since it could be equal to, I'm going to use a closed dot. And remember, that shows that I am including 10 as a possible value for x, because x could be equal to 10. And then I'm also going to include all the numbers less than 10. So all the numbers to the left are all less than 10. All right, we'll look at one other example like this, and then we're going to move to the other part of our lesson today. All right, this is the second example we're going to do on negated inequalities, and this is kind of the opposite of what we just did. This example, it gives us a graph, and it wants us to write both an inequality, like we've done before, and a negated inequality. And so we need to look at our number line here, look at the graph on it, and let's figure out what it's saying. First of all, we've got an open circle, an open dot on 3. So since it's not filled in, we know that x is not equal to 3. So if x is not equal to 3, then it could only be less than or greater than. Let's look at what our arrow is doing. Our arrow is pointing this way, to the left. And it's pointing at all the numbers that are less than 3. So that's what this graph says. This graph says x is less than 3. Remember, this is the less than in. So x is less than 3. That's what our graph says. That's the inequality. But we also want to write a negated inequality. So if x is less than 3, then it cannot be the other 2 possibilities. It cannot be greater than or equal to 3. And since it can't be, I should put a slash through it. So these two things actually mean the same thing. Two different ways of writing the same statement. This is an inequality. This is a negated inequality. If x is less than 3, it cannot be greater than or equal to 3. All right, like I said, there is another part to this lesson, so we're going to switch gears a little bit, and we're going to look at ratios a little bit more. Let's look at that. All right, so the next part, I said we're switching gears a little bit. We're going to ratios, and we're looking at some advanced ratio problems. Because what happens is, what we've been doing so far is just basic, simple ratio problems that did not involve any totals. This time we're going to look at some that do involve totals. And as an example, we're going to say that we have a certain amount of marbles, okay? We're going to say we have a bag of marbles. We have some red ones. We have some blue ones. And in that bag, the ratio of red marbles to blue marbles is 5 to 7. All right, now we've done problems just like that before. Here's where things get a little bit different. Let's say that we actually have a bag of marbles, and instead of me telling you how many red ones are in it or how many blue ones are in it, I'm going to just say that there are 700 marbles in the bag. We're not used to doing that. We're used to just knowing how many red or how many blue. So what we need to start doing is when we see ratios, we need to start realizing that there is another piece of information that a ratio gives us. It's not thrown out there obvious, but we can figure it out. Because if we look at this ratio here, 5 red marbles, 7 blue marbles, there's another number hidden in there, and that would be the total number of marbles. Because in a group of 5 red marbles and 7 blue marbles, we actually have 12 total marbles. And so that's the third number we need to start getting whenever we see these. So we're going to look at one example like this, and then we'll be done. Let's take a look. All right, here's the example we're going to look at. This is the ratio we just talked about, a ratio of 5 to 7. We said that we're talking about marbles. We have 5 red marbles for every 7 blue marbles. What I've done is I've gone ahead and written down the relevant information that we can glean from that. Whenever we see a ratio, we should remember it's telling us two things, but it's also in a hidden way telling us a third thing. In this case, it's telling us that we have 5 red marbles for every 7 blue marbles. But it's also telling us that within that small group, we have a total of 12 marbles. So, in our problem today, it tells us that we have a bag full of 156 marbles. It wants us to find out of that total number of marbles, how many are red. So, what's happening is the problem is actually telling us our ratio, because it's telling us that we do know something, and it's asking us about something else. So those are the two things we're comparing. We're comparing what we do know and what we don't know. So when I'm going to write my ratio today, that's what I'm going to write. So think about what the question is asking us. We have an example on the bottom page in our books, and it asks us, out of a total bag of 156 marbles, with this ratio, how many of them are red? So it's asking us about the number of red. We don't know that. So in my ratio, I'm going to have a certain amount of red marbles. It's telling us we have a total of 156 marbles. So what we're doing is comparing red marbles to total marbles. And so we're going to write a proportion made up of two ratios that each have red marbles over total marbles. So let's write that. First of all, let's use the ratio it gives us. Remember, we said that there are 5 red marbles for every 7. Now, I don't want to write 5 to 7. I want to write red to total. So I'm going to say there's 5 red marbles for every 12 marbles of any color. So out of every 12, there's 5 red ones. And I'm going to say that's equal to the ratio for the whole bag. Because in the whole bag, I have a total of 156 marbles. And so I'm still going to have a ratio of red marbles, even though I don't know how many. I'm going to write it as R over the ratio, the number of total marbles. 156. So notice my ratio is the same throughout the problem. Red to total, red to total. And since I want to find R, I cross multiply. I do 12 times R and get 12R. I also need to do 156 times 5. And since I don't know my 156 times tables, I'm going to multiply that very quickly. By the way, if you know your 156 times tables, good on you. I'm proud of you. I don't know. But now I have 780. So I get 12R equals 780. Remember, it's a proportion, so we just cross multiplied it. And now to get my answer, I simply divide 780 by 12. And that will give me R equals, and again, if you want to do some long division, you can. I'll give myself a little bit of room here. 780 divided by 12. 12 will go into 78, about 6 times. And 12 will go into 65 times. And so the number of red marbles is actually 65. So out of our total number of marbles, 156, we found that there are 65 red marbles. All right, that's it on advanced ratios. Practice those a little bit. Once you get the hang of them, there's nothing to them. I hope this helps. Any questions or comments, feel free to add them in the comment section, and go ahead and subscribe while you're at it. We'll see you next time.